Hi, and welcome to part 2 of our recorded lecture about network flow problem. You'll remember from last time, I think this is about where we ended up. We talked about the network flow problem, we looked at two different algorithms for it, and the second one we came up with Edmonds-Karp. We were able to prove a time bound for this. But even then, it ended up being a pretty expensive algorithm. Right there on the screen, you can see it is, well, at least it has a runtime that doesn't depend on the value of the maximum flow, but it's still pretty expensive. Measured in vertices, it could be up to O of v to the fifth for a dense graph. So we were going to come up with a better approach to this, and I think I mentioned last time, there are a class of algorithms that can achieve better performance. They work a little bit differently. They're called push-relabel algorithms. And the first thing they do is they relax one of our two big constraints. Remember, we had a capacity constraint that said you can't push more commodity across an edge than the weight of that edge, or we interpret the weights as capacity limits on the edge. And it keeps that, but it relaxes flow conservation. That's the idea, that previously that was the constraint, that you can't have more flowing into a vertex than you have flowing out of the vertex. At least that's true for everything except the source and the sink vertex. So since we're going to relax the flow conservation requirement, or we're going to permit vertices to overflow, to have more flowing in than flows out, we'll call this a preflow. It's just a difference in the terminology. We'll use the same notation we used before. So in the example graph I've got at the bottom of this slide, we've got a graph. The number after the slash is the capacity constraint, and the number before it is the number after the slash is the capacity of that edge, and the number before it is the flow. And in making up this example, I tried to adhere to the capacity constraint everywhere. So you can see this edge right here has a capacity of 5, and we only have 2 flowing across it. This one has capacity of 9, and we only have 8 flowing across it. But I deliberately violated flow conservation in a few places, like this vertex D. In fact, all of the red vertices are overflowing. So this one has 8 units, or 8 units of commodity flowing in, but it only has 1. There's 1. There's 4 more, so that's 5. There's 2 more, so that's 7. So it has 8 flowing in and 7 flowing out, so it violates flow conservation. So the idea is we are going to temporarily permit vertices to overflow as we're trying to figure out the maximum flow, and then we'll fix that before we're done. And this will allow us to, one way you can think about this is it will allow us to converge on a maximum flow faster, because we're not going to be increasing it by just one path every time. We can effectively push a lot of flow at once in the direction from the source to the sink. So we've got a new name. We're going to call this a preflow, just like a flow, except it doesn't have the flow conservation constraint. And we got a new notation at the bottom. E of u is the excess flow at vertex u. So that's the amount that's flowing in, but it's the amount that's flowing in but not flowing out. So it's the, for everyone except the source and the sink, it's the total amount flowing in minus the total amount flowing out. These algorithms, all of the push-relabel algorithms, depend on this measure of height for every vertex. So every vertex has an integer height, and I think there's sort of a physical comparison for this. When we change the flow, we're going to think of it as always wanting to flow gently downhill. I'll give more, I'll say exactly what I mean about that in a moment. But here the height, like I said, it's an integer. Most vertices will start with a height of 0, and then as we run the algorithm, we'll gradually increase their height in an effort to kind of push more flow toward the sink, and then eventually to push any excess flow back into the source, so that our final solution is a legal flow until we have our final solution. Like I said on the previous slide, we'll call it a pre-flow. But when we're done, we want a legal solution to this problem. So we need no overflowing vertices. So the height will help us decide. It'll kind of give us an extra rule, maybe a couple of extra rules for when we can push more commodity out of a vertex and into another vertex. So like you probably don't need me to say this, but like I'm showing in my picture, vertex V, I'm showing with a height of 1, and vertex U has a height of 3. Like its name implies, the push-relabel algorithm really depends on 2 operations. That's where its name comes from, the push and the relabel operation. Push is for moving flow or moving additional commodity from one vertex to another, and relabel is what changes the height. So let's talk about push first. You can't always do a push. There are rules for when you can increase the flow across an edge. That's what I'm trying to illustrate with my little picture. First of all, well, you can push from vertex U to vertex V, provided there's an edge from U to V in the residual graph. And when we say that, we really mean an edge with some residual capacity. So an edge that's already saturated doesn't help. You can't use it for the push operation. But if there's a non-zero capacity edge in the residual graph from U to V, then maybe you can do a push. That's one of the requirements. Vertex U, the vertex you're going to push from, has to have some excess flow, so it has to have some additional commodity that's flowing into it that we could push to V. And then finally, the height. The height matters. And this is what I meant when I said we're going to push commodity gently downhill. You can only push when U has a height that's 1 more than V. And the reason for this is it'll eventually, we're not going to show it in this lecture, but that's what would eventually let us prove a running time bound on this. The constraints on the height can give us a limit on how many push and relabel operations this algorithm can do. And you can also think of it as, well, I've got a picture that shows this a little bit later. You can think of it as kind of wanting to push to neighbors as early as you can, as soon as the height permits that. And maybe that'll make more sense when we have a little bit more of an example. All right, so the push operation doesn't say it on my slide, but I didn't tell you what it actually does. The push operation, if all these constraints are met, and again, just reading them off the slide, there has to be an edge from U to V in a residual graph, a non-zero weight edge. U must have some excess flow, and the height of U must be 1 greater than V. And if all those conditions are met, then you're going to push as much additional commodity as you can from U to V. So you're going to increase the flow across this edge, pointing to it right here, by as much as you can. That'll mean either until that edge is saturated, until you've used all of its residual capacity, or until U isn't overflowing anymore. So whichever of those comes first. If U has plenty of excess flow into it, then you can saturate. You may be able to saturate this edge and still have some excess flow at U. Or if U just has a little bit of excess flow, you may be able to push all of that across this edge, increase the flow on this edge, and then still have some residual capacity on this edge. The push-relabel algorithms have 2 operations. This is the one that actually changes the flow. My label at the top of this slide is wrong. It should say relabel operation, because that's the one we're talking about here. So the other operation is the relabel operation. And that's just a rule for kind of the bookkeeping of the algorithm. It says when you can change the height of a vertex. And like my picture tries to show, the relabel operation happens when, or you can do the relabel operation if there's some vertex U that's overflowing. So notice both of these operations only apply when you have a vertex that's overflowing, and it has an edge to a neighbor V that has some residual capacity. And in that case, you raise U's height to be one more than the height of its lowest neighbor. So I think of this as raising it just enough, or increasing its height just enough so that it could later do a push to that neighbor. So the push operation, backing up, the push operation actually increases the flow across an edge. The relabel operation raises a vertex, an overflowing vertex, just enough so that I could maybe do a push in the future. I mentioned the height is sort of, it's an additional constraint for when you can do the push operation. And I've got some pictures here that try to show what the rules are for the height. You can think of the height as kind of matching how you might think of water flowing from one vertex to another. If an edge goes from if a residual edge, like in my picture here, if it goes from a lower vertex up to a higher one, there's nothing wrong with that. It's just you can't do a push on that edge. You can only push gently downhill. So it's fine to have edges that point up or that go from a lower vertex to a higher one. You just can't push across those. It's fine to have edges that are horizontal, that go from a vertex to another vertex of the same height, but you still can't push across that edge. It's fine to have an edge in the residual graph that goes down by 1 in height. So like my picture shows, it's fine if vertex U is at some height and vertex V is 1 lower. Is it at a height that's 1 lower and there's an edge between them with some residual capacity. And like I said a couple of slides ago, this is the only time when you can push some additional commodity across that edge. What you can't do is this. We want to never let, in fact, the operations we're doing will never let a vertex be more than 1 unit higher than its neighbor. I could probably say that better. My picture kind of shows this. If there's a residual edge, so if there's an edge with some residual capacity going from U to V, then we will never let U's height be more than 1 more than V. Why is this? Well, this gets used in proving the runtime bound of this algorithm. But if you want to try to think of it intuitively, you can think of, well, if there's a residual edge from U to V, so there's, and U is overflowing, then my chance to push from U to V is when U is only 1 higher than V. If I let U get more than 1 higher than V, then I kind of missed my chance to push any excess flow from U to V. I should have pushed that earlier. I should have pushed that when U was a little bit lower. So we'll think of trying to increase the height of vertices gradually. And you can kind of see that in the rules that we've talked about. We only increase the height during a relabel operation. And we only do that we can only do a relabel operation when a vertex is overflowing and it's lower than any of its neighbors. And when I say any of its neighbors, I mean any other vertex to which it has an edge with some residual capacity. And then when we do that, I'll back up to show you the relabel operation, the one that I'm talking about. So we only relabel when we've got some excess capacity and we can't push it across any of the edges, any of the outgoing edges, because the heights are, because we're lower than any of those neighbors that we've got outgoing edges to. And even then, we increase the height as little as we can. We increase it to just 1 more than any neighbor to which we have some residual capacity. So that's why I think of this as increasing the height gradually. When we're 1 higher than any of our neighbors, we'll push to all those neighbors that we can, and then we'll only increase our height beyond that when we still got some excess flow, and all of those neighbors, all the edges to those neighbors have been saturated, so we have to find new neighbors that we can push to. I've got an example that tries to illustrate this. Unfortunately, with the height, it's a little hard to show a non-trivial example showing the structure of the graph. and the structure of the height, or sorry, the behavior of the height at the same time. So I picked a really simple graph here. I've got, and there it is right there. I've got a source vertex, I've got two vertices in the middle, and then I've got a sink vertex over on the right. And just looking at this, you can tell the max flow must be 3. This 8 edge gives you plenty of capacity, 5 narrows it down a little bit, and 3 narrows it down a little bit more. And since this is kind of the bottleneck on the way to the sink, that's going to restrict our flow. That's going to be the maximum flow we can have. The reason I picked just a kind of a linear graph like this is I can show the graph left to right, and I can show the heights by moving the vertices up and down, and we'll do that as we look through this example. Just looking at my notes at the bottom, like I said, we can just look at this and see that the maximum flow is going to be determined by this edge. And here you can also see the max flow min cut theorem. It's kind of trivial here, but another way of thinking of it is, well, if I put a cut right here between vertex B and T, that would separate the source from the sink, and the total weight across that cut, 3, is my maximum flow. It's sort of the narrowest bottleneck through this graph. So we've talked about how the push-relabel algorithms work. We've talked about the definition of this height function and the rules for thinking about height. But we haven't talked about how to initialize it. It's an important part of the algorithm, and now we've got enough here that I think we can show it. So for the push-relabel algorithms, we start with a flow, or we start with a preflow that kind of pushes as much as it can to the neighbors of the source. So when we initialize the preflow, we take all of the edges out of the source, and here it's just this one edge, and we saturate them. So in this example, A is the only neighbor of the source. If we had more, we'd do this for every one of them, or if we had more edges going out of the source, we'd do that for every one of the edges. We saturate this edge, so we give it a flow that's equal to its maximum. And that means that this neighbor of the source is probably going to be overflowing. The only way it wouldn't be is if it happened to be the sink vertex. So typically, let me try to say this clearly. You initialize the preflow by saturating every edge out of the source. And in general, that means any vertex that's a neighbor of the source is going to be overflowing at this point. In this case, I just saturated this edge. I haven't thought about these other two yet. And you can see vertex A, I went ahead and colored it red like we did in the previous examples to kind of remind us that it's overflowing. It's got 8 units of commodity flowing in and 0 units of commodity flowing out. In this picture, this is kind of showing the flow and the capacity. If you wanted to look at the residual graph instead, remember that shows how much remaining capacity there is between any pair of vertices. The residual graph would look more like this one at the bottom. I've still got 5 units capacity unused here. I got 3 units of capacity unused here. I saturated the edge from S to A, so I didn't draw that edge because I can't use it, at least not for now. But I have 8 units of residual capacity going back the other way. That's like saying if you wanted to, you could take back some of that flow. You could push some commodity back from A to S. So that's how we initialize the preflow in these push-relabel algorithms. How do we initialize the height? Well, every vertex starts out with a height of 0. And I've tried to show that here. In fact, we'll use the same kind of picture as we work through an illustration of this algorithm. Every vertex starts out at a height of 0, except the source vertex. It starts out at a height that is the same as the number of vertices. And later you'll see that's kind of a maximum height. I started to say that, but then I stopped because maybe that's not the best way to describe this. Here's maybe another way to think about it. If S is at a height of V and T starts out at a height of 0, even if you had sort of the longest possible path on the way from S to T, and you were going to let some flow sort of trickle down that path, you've still got enough of a height difference between S and T that all the guys in the middle could sort of make a chain that was going down by 1 each time, or at least you've got enough height that you could do that, and you could drain flow all the way to the sink vertex. So think of S as being high enough that you can get as much flow as you want from S to T, still following the rules for the height. You remember the rules for the height were, there's really only one constraint, and that is you can't have an edge in the residual graph that goes down by more than 1. At first, you might look at this graph and you might say, oh, it violates that constraint, because here's an edge and it's going down by 4 instead of 1. But that's one reason I showed the residual graph. This edge is saturated, and even though I drew it kind of pointing from source to sink, if you really looked at the residual graph, it would look like this picture here. The forward edge from S to A has been saturated, and I didn't explicitly draw the residual graph here, but in this edge, if you think about the residual graph, there's not really an edge pointing this way. That one's saturated, but there is an edge pointing back from A to S. And remember, edges can go up as much as you want in height, or there's nothing wrong with them going up. That's just an edge you can't push any additional commodity across. They just can't go down by more than 1 unit. So I think we're okay here, because again, this edge, there's not really an edge from S to A in the residual graph. All of that edge's capacity has been used for now. Over here, these two edges are staying the same height, so they satisfy our rules for the height. I started to say how you initialize the height, and I almost finished saying that. I think it's down at the bottom of the slide. So everybody starts out with a height of 0 except for the source vertex, which starts out at a height of the number of vertices. The height of S and the height of T are never going to change, but the height of every other vertex can slowly go up as the algorithm runs. Really, from the definition of the relabel operation, you can tell that S and T are never going to be able to change height because I can only do a relabel operation on a vertex that's overflowing. If you back up and look at the constraints for the relabel operation, it says you can only do this when you have a vertex that's overflowing. And S is never going to be overflowing. We kind of pretend it has as much commodity as you want to take from it. And T is never going to be overflowing. We kind of pretend it can absorb as much commodity as you want. But the vertices in the middle can be overflowing, so that's a chance to relabel them. And remember, relabel just moves them up in height. So you can think of these vertices in the middle as occasionally getting a chance to move up so that they can later push additional commodity to one of their neighbors. So backing up a slide, we talked about how to initialize the preflow. We talked about how to initialize the height of all the vertices. And now we can just start running the algorithm. The algorithm now that we've given all the background, it's really easy to describe. A generic push-relabel algorithm it does what we just talked about. It initializes the preflow, sort of saturating every edge out of the source and setting the heights of almost everybody to 0 except the source vertex. And then it just repeatedly does a push or a relabel operation. It picks, if any of those operations are doable, it finds either a vertex that it can relabel or an edge that it can push some additional commodity over, and it just does that until it can't do any more push operations. We're not going to go over it in class, but there is a proof that once you've finished this, once you've done all the push and relabel operations you can, this algorithm has to converge to a legal maximum flow. So its flow won't even be a preflow anymore. It'll satisfy the flow conservation. I also mentioned, we'll come back to this later, that push-relabel is really a class of network flow algorithms. And here we're kind of showing the generic version of the algorithm. Different variants or different types of push-relabel algorithms might have stricter rules for when you can do a push and when you can do a relabel. Also, like we'll say later, this algorithm makes it look like you'd have to hunt for an available push or relabel operation that you want to do next, but it's not too hard to implement this so that it can always efficiently find some new operation that it might want to do next. All right, so I think we're ready to see the algorithm work now. The picture at the top is the same one we had from a couple of slides ago. It shows the initial height of all these vertices, and it shows the flow across each edge. And if you just look at that top graph, you can see I can't do a push operation right there. I can only do that when I have an overflowing vertex. Well, A is overflowing. I got a residual edge to one of its neighbors, or I've got an edge with some residual capacity, and there's one. But I can only do that, but I can only do a push when it's one higher than any of its neighbors. This is the only overflowing vertex, and I can't push right now, but I can relabel. Remember, relabel is when you have an overflowing vertex. It's got an edge to one of its neighbors with some residual capacity, and for the relabel operation, you increase the height of that vertex, here vertex A, to be one more than its lowest neighbor to which it has some residual capacity. So for relabel, that means, like my bottom picture shows, I can move A up to a height of 1. Again, one more than the height of the lowest neighbor to which I have some residual capacity. And here, hopefully you can look at this and say, oh, you're doing that so that you can then do a push operation. Now you can push some additional capacity to B, and that's what I do next. My picture shows A had 8 flowing in and 0 flowing out. I've got enough, so it's overflowing by 8. I've got plenty to saturate this edge, and now I'm pushing 5 units to B. And notice A and B are both overflowing now. A has 8 flowing in and 5 flowing out. B has 5 flowing in and 0 flowing out. All right, so we're simulating the generic push-relabel algorithm. What can we do at this point? Well, A has a residual edge. You have to imagine it in this picture, but it's got a residual edge going back this way. This edge is saturated, so I can't use that. And A is overflowing. B is overflowing. It's got a residual edge going this way, and it's got a residual edge going back to A. So we could take back some of that 5 if we wanted. I can't push to T right now, but if I do the relabel operation, so B is eligible for relabeling. It's got a height of 0. It's overflowing, and I've got an edge that with some residual capacity that goes to one of my neighbors. So if I relabel B, its height goes up by 1, and now I can push some additional commodity to T. So this bottom picture shows doing the relabel operation, and then I can push. I've got enough overflowing at B that I can saturate that edge going to T. And now if we look at the whole flow, we got 2 overflowing vertices in the middle. But I have at this point gotten as much commodity as I can to T. T has 3 flowing in, and we pretend that T can have as much flowing in as we want. So T has as much as I can. Let me try and say that better. I'm pushing as much commodity as I can to T at this point. But I'm not done because I don't quite have a flow yet. At least I'm not following the rules of a flow. I'm following these relaxed rules for a preflow, because A and B are still overflowing. The nice thing is, for this algorithm, I don't have to do anything extra to fix that. I just keep running the algorithm. I keep looking for push and relabel operations that I can do. A and B are both overflowing. I can't push from B right now because this edge is saturated. And if you think about B, there's a residual edge that would let me take back some of these 5 going from B to A. But I can't push across that yet because B's height is the same as A's. Same thing, A is overflowing. I could take back some of the flow from S. I could use the residual edge of weight 8 from A back to S. But I can't do that because of the height rule. So the next thing I have to do is, and the next thing I can do, is a relabel operation. And here my picture starts getting a little bit taller. Let's back up and say, all right, so if I had to relabel, I could pick A to relabel. I want to make it 1 higher than its lowest neighbor, to which it has a residual edge, and that's kind of what I was saying a moment ago. There is a residual edge with capacity 8 going from A back to S. So if I relabel, and that's my lowest neighbor that I could push some additional commodity to. So if I relabel, oops, I went the wrong direction. So if I relabel A, its height goes up to 5. Now, next, I could choose to push from A down to S. And that might be what the algorithm would do. I'm going to take a shortcut. The algorithm could do this. It's just the generic push-relabel algorithm doesn't guarantee that this is what it would do next. But trying to finish this example more quickly, if it chooses to relabel B, I think the algorithm will finish a little bit faster. B is overflowing. There's a residual edge going back this way. You can take back some of that flow of 5 from B to A. So if we relabel B, it's going to go up to a height 1 greater than that neighbor, so its height will go up to 6. And now we're almost done. B is tall enough or is high enough that it can push some residual, or can push some of this flow back to A. And if that's what we do next, if we do a push from B, this flow goes down to 3. B's not overflowing anymore because it has 3 flowing in and 3 flowing out. So it's not really, at this point, it's not eligible for any pushing or relabeling. But A is still overflowing. It's got 8 flowing in and only 3 flowing out. This edge, the residual edge going from A back to S, has 8 units of capacity remaining. I could take back up to 8 units of flow going from S to A. And if I take back 5 of those units of flow, if I essentially, my picture doesn't show it super well, but if you think of this flow of 8 out of 8, meaning, oh, you got a residual edge from A back to S with a capacity of 8. A is overflowing by 5, and there's enough residual capacity from A back to S to push all 5 of those overflowing units back to S. So that's what the algorithm's going to do. Remember, whenever you've got an overflowing vertex and you've got an edge with some residual capacity, you push as much as you can across that edge. And that means until either the edge is saturated or you've used all of your excess flow. And in this case, backing up, the excess flow into A is 5. We can push all of that back to S. And at this point, we're done. The reason I say that is our 2 operations depend on finding an overflowing vertex. And there are no more overflowing vertices. A and B both satisfy the flow conservation requirement now. So at this point, the algorithm would terminate. And you can see in this case, it found a maximum flow, and before it was done, it turned it into a legal flow. If we I looked at showing the proof for this, and I'm not sure we have time to go through all of that, but the proof for this, for the running time of this algorithm, really depends on showing how many push and relabel operations could happen. And if you remember when I first started showing this example, I try to talk about how, well, initially, as you're pushing from the source to the sink, you can imagine that you've got enough height difference between those that you could have a chain of vertices getting shallower and shallower on the way from S to T. Here you can see what's going to happen at the end of this algorithm. If you've got some overflowing vertices, they're gradually going to get pushed up above the height of S so that any excess flow they have into them can drain back into S. And once that's all happened, the algorithm is going to be able to terminate, because if you don't have any more overflowing vertices, you can't run any more push or relabel operations. I don't think we've really proven that, but I've tried to give you some intuition about how you can think about it. And with those rules for the height, like I said, you can put a bound on the maximum number of push and relabel operations that you can do. I didn't mention this earlier, but I should have. Notice that, well, I was going to say, what's the running time of a push and a relabel operation? A push operation, as long as you know what vertex you're going, or sorry, what edge you're going to push across, that should be a constant time operation. A relabel operation, you might imagine, is more expensive because you might have to look at all of your neighbors and find the lowest neighbor to which you have some residual capacity. And if you did it that way, that might take, I guess, at worst, V time if you had to look at every possible neighbor. But instead of looking at it a vertex at a time, if you find that edge, I feel like I'm doing a bad job of explaining this, you can detect relabel operations more efficiently than just looking at a vertex and then looking at all of its neighbors. And if you do that, I think you can get that down to a constant time operation also. With that, we can show a bound on generic push relabel that ends up being V squared times E running time. And that's better than if you rewound a bunch of slides and compared that against our previous algorithm. We said it ran in worst case V to the 5th time. If we wanted to compare this, we could say, well, for a dense graph, V squared times E is no worse than V to the 4th. So we're already doing a lot better than that previous algorithm. This is for a generic push relabel, one that doesn't place any additional constraints on the order of push and relabel operations. There's a particular policy for push and relabel called relabel to front that says the order in which you might do push and relabel operations. And if you specialize the algorithm like that, you can get the runtime down even better. Relabel to front runs in time O of V cubed, and that's much better than the V to the 5th we started with. I didn't put relabel to front in the slides. It's described in your book. It's a type of push relabel algorithm that just puts additional constraints on the order that you do these operations. All right, we've talked about 3 different algorithms. At least we've gone through 3 different algorithms for solving network flow. I want to show you one more thing that you can do with network flow. I mentioned when I introduced this problem, one nice thing about it is it's very adaptable to solve other problems, even ones that might not look like graph problems initially. I was going to show one easy example of how you could do that, and that is solving the maximum matching problem. Maximum bipartite matching. Now you remember a bipartite graph is like the one that I'm showing down at the bottom. It's got vertices that come in 2 categories. I've drawn some vertices on the left, and the other category we'll put on the right. And all of the edges go between the categories. There are no edges that go within a category. And like the name implies, so like my picture shows, maximum Bipartite matching works on a unweighted, undirected bipartite graph. So like I've drawn here, there are no arrows on the edges. There are no weights on the edges. I just want to find a subset of the edges that pairs up as many vertices on the right as I can with vertices on the left. So like the name suggests, I want to find a matching, a pairing up of vertices over here with vertices over here. So each one over here is paired with, as many as I can over here, are paired with a unique vertex over here, and the same, as many vertices as I can over here are paired with a unique vertex over here. So in my original graph, I may have a lot of edges coming out of certain vertices, but for the matching, I just want each vertex on the left, or at least as many as I can, vertices on the left over here, to be paired up with vertices on the right, and as many vertices on the right as I can to be paired up with vertices on the left. What can I tell you about this problem? Well, we could obviously come up with an exponential time algorithm for this. If you just tried to look at subsets of the edges, you could remember the maximum one you saw, or at least the largest one that satisfied these constraints, but that'd be awfully expensive. It turns out you can solve this problem in polynomial time, and we don't even have to invent a new algorithm for it. We can adapt any of our network flow algorithms to solve this by thinking of it as a network flow problem. Imagine you, and this picture shows how you can turn it into a network flow problem. Imagine, all right, so this stuff in the middle, that's my matching problem. I'm going to take each edge that was part of the matching problem, and I'm going to turn it into a directed edge from the left side to the right side with a weight of 1. I'm going to make a source vertex, and like my picture shows, I'm going to give it an edge that goes to each vertex on the left, each of those edges with a weight of 1, and I'm going to do the same thing over on the right, going to the sink vertex. So you can think of, and that's really all I'm going to have to do to convert this to a max flow problem. You can think of the when I find a maximum flow through this graph, I can push up to 1 unit of capacity to each of these vertices on the left. And then, as long as they can find a unique vertex on the right to push that 1 unit of capacity to, they're getting it a little bit closer to the source, or sorry, to the sink. If a vertex can get 1 unit, if a vertex over here on the left can get 1 unit of commodity to a unique partner over here on the right, I've got an edge to get that the rest of the way to the sink. As long as I can match up, well, I'll say, as long as I can match up every vertex over here with a unique vertex over here, I can get all of that commodity the rest of the way to the sink. I hesitated a moment ago because I had started saying this wrong. Even if I can't pair up everyone over here with a unique partner over here, as many of them as I can, for each vertex over here that I can pair up with a unique vertex over here, that'll let me increase the flow to the sink. Notice if I tried to pair up both of these vertices, say these two that I'm pointing at here, with the same vertex over here. So each of them could push 1 unit of commodity across, say this guy could push 1 unit of commodity across this edge, this guy could push 1 unit of commodity across this edge. If those both went to the same vertex over here, this edge out of them would be a bottleneck. So the maximum flow can't pair up 1 vertex over here with 2 different vertices over here, because the capacity constraint over here would prevent more than 1 unit of flow from getting the rest of the way to the sink. The same thing happens over here. In a maximum flow, I can't have this vertex sending a unit of commodity to here across this edge any unit of commodity across this edge because it only has one unit of commodity coming in, so the best it can do is send that unit of commodity to one other vertex on this side. So that's a rather informal way of trying to argue why, if you build this network flow graph, the maximum flow that it finds must pair up as many vertices over here on the left as you can with one corresponding vertex over here on the right. And we already saw, I mentioned a moment ago, there's an obvious exponential time algorithm for this. But if you just build this slightly larger graph and run one of our existing network flow solutions on it, then you've got a polynomial time solution for this problem. We mentioned this when we were talking about NP completeness. Maximum flow is interesting because, well, we just argued it has a polynomial time solution via network flow. So it's easy to find a maximum matching. But if you look at the counting version of this problem, it is still hard to count the number of unique solutions. What I mean is, well, if this is your maximum matching problem, here's an example of a maximum matching. It pairs up as many vertices on the left as we can with vertices on the right, but it's probably not the only solution. If we wrote an algorithm to go in and count how many solutions there are, then this problem starts to look just as hard as any NP-complete problem. It's just as, so finding a solution is easy, but counting all solutions looks a lot harder for this problem. So I think that sort of shows that it's an interesting problem in terms of complexity. That's all I got to say about maximum matching. We covered one, so today we covered one more algorithm for network flow, and we covered the maximum matching problem and an application of network flow to that. We didn't look at it, but if you're interested, I've got an illustration, an online example of running maximum matching and turning it into a network flow problem. So if you want to watch that in action, I think you'll see what we were trying to talk about. That gets us through all of network flow. Thanks for your attention, and I'll see you when it's time for the exam.